So we are in Statistical Rethinking, second edition, chapter 11, and we'll cover questions 11M3, 11M4, and 11M5 in this video. So for 11M3 and 11M4, we are meant to explain why the logit link is appropriate for binomial generalized linear models. And so we'll answer that. And then similarly, we're supposed to explain why the log link is appropriate for Poisson generalized linear models. Okay, so the answer is similar to both of these, and that's why we're lumping them together. The book talks about this in a little bit of detail. There's a lot that can be said about link functions. Most of that discussion is omitted from this book, and maybe just as well. It's technical aspects of just kind of the mathematical underpinnings. That's interesting and worth learning about, but not critical. So let's look at the logit link first. Okay, so the basic answer is just simply that in logistic regression, usually for binomial models, we are trying to model a parameter, and we'll call it P in this case, that is constrained between 0 and 1. Okay? Now the logit link, which again is just the log odds, achieves this by mapping values of our linear function, when we'll just generically call it x beta, but it can be a very complicated function, to values between 0 and 1. Right? And so the book in figure 10.7 kind of demonstrates this. Right? So we have our x beta, we have our linear model that can have any number of values, okay? But then when we take the values here of our log odds, okay, of our linear model, we get out a value that is between 0 and 1, and that's it. That's the answer, right? So a logit link constrains the values of the outcome between 0 and 1, right? And so like for a binomial regression model, we're often trying to figure out the parameter value P, where P is like a probability of something occurring, and probabilities are constrained between 0 and 1. Okay, so next, the log link function. Okay, so there's the answer rhymes with the binomial regression, logistic regression, but in Poisson regression, we're usually modeling a model parameter, call it lambda, that's non-negative, okay? And so the log link function takes whatever value we have in our linear model, x beta, and ensures that it is greater than or equal to 0, okay? Right? So if this is the output of our linear model, the log link function makes sure that it sticks to values above 0. Okay, so for count variables, right, we can't have less than 0, right? And so while our linear model may produce values less than 0, that's an impossible value if we're counting things, right? We have to be at 0 or above, and so the log link function achieves that. Okay, so a couple of things here before we move on to the next one, which is 11M5. Link functions are actually pretty flexible. You can use an array of different link functions with your generalized linear model for whatever variable. It's just that certain ones make more sense, are more interpretable. Okay, and often, but not always, but often the more interpretable link function falls out of the math for these types of distributions, for these exponential distributions, and it's often called the canonical link function if you want to do some reading. But not always. We can mix and match link functions, and sometimes it makes sense to do so. Sometimes it doesn't make sense to do so. But for instance, what is it? I believe it's the gamma function. I believe that the link function is like the inverse of the parameter, but that rarely gets used. It's often just the log function. So even though the inverse function is the canonical link function, I believe it's for the gamma distribution, often just the log link function is used, and it's interpretable. So, okay, so having said that we can kind of mix and match link functions, although it doesn't always make sense to do so, we come to 11M5. So what would it imply to use a logit link function for the mean of a Poisson generalized linear model? Can you think of a real research problem for which this would make sense? Okay, so what would such a model look like? So it would be where we have an outcome variable that is distributed as Poisson, okay, where Poisson has its parameter lambda, and in a Poisson distribution, the mean is lambda, so the expected value is lambda. All right. So this model would have a logit of lambda, which would be this, and that would be equal to the linear model. Okay. So then this would imply that the expected value of y, again lambda, is bounded between 0 and 1, right? Just like for above, where we had this, right? For our binomial regression, we had the logit of the parameter p, and we used the logit function because the logit link because it bounds p between 0 and 1. This would bound lambda between 0 and 1. Okay. Now that probably doesn't make sense because we have this, we'll call it a count variable, where it is bound between 0 and 1, I can't think of a reason that we might really use that in practice. If we did have something that was bound between 0 and 1, we would probably use a binomial distribution. Okay, so anyway, that is 11M3, 11M4, and 11M5.